Good afternoon, everyone. My name is Kim Mazeros, and I'm the Ergonomics Research Coordinator at CRE-MSD. And on behalf of our director, Dr. Jack Callahan, I would like to thank you for joining us today. We are pleased to welcome you to this webinar on cognitive workload in the workplace toward integrating mental demand measures into ergonomics assessments. We would also like to acknowledge and thank the Ministry of Labor, Immigration, Training, and Skills Development for their funding, which supports the delivery of these webinars, as well as our presenters for sharing their expertise. Before we begin, I'd like to go over a few administrative details. This webinar is being recorded, and a link to the recording will be provided along with the presentation slides shortly after today's session. Today's webinar format will consist of the presentation, followed by 10 to 15 minutes for question and answers with our presenter. Please enter your questions into the Q&A feature. I will relay those questions to our presenter, combining similar questions where appropriate. If you experience any technical issues during the webinar, please send us a message in the chat feature. Following the webinar, you will receive a link to an evaluation survey. One of our key measures is understanding the impact of our webinars, so we greatly appreciate you taking a few minutes to complete this short survey. Now it is my pleasure to introduce today's presenter, Dr. Francesco Biondi. Francesco is an associate professor in the Human Systems Lab at the University of Windsor. He leads a group of cross-disciplinary researchers focused on the development and assessment of human-centered technology in automotive, manufacturing, and healthcare. He serves as an expert witness in legal cases involving driver distraction and driver interaction with autonomous vehicles. Francesco, thank you so much for taking the time to share your research with us today. Now over to you.
Absolutely. First of all, thank Bettina and the Kim and the group of CRE-MSD for having me speak to you today. Today's talk is about better understanding how to integrate cognitive workload in the workplace, what research is telling us, and maybe what are the steps that are missing in order to fully integrate this knowledge into a practical intervention. Before we start with the agenda, I want to thank CRE-MSD, of course, again, not only for the opportunity being given me today to speak to you, but also for the funding that they provided my research group over the years. I also want to provide special thanks to Atlas Copco. They've been very generous with their funding to the work that we do in cognitive workload and manufacturing, TRQSS, for their collaborative efforts, and of course, NSERC, again, for their generous funding. Special thanks to Noor Al-Azari. She's a first-year PhD student in my lab. She's been instrumental in putting together this presentation. And then last but not least, I want to thank the ergonomics group at U Windsor, with special thanks to Dave Andrews and Joel Court for their support and mentorship over these years. So there is a missing link between what we know of cognitive load research and workplace assessment practice. There's an ever-growing body of research on how to measure cognitive load in different environments, healthcare, manufacturing, driving, etc. But there is a missing connection between how we are able to translate that into workplace assessment practices. So with this presentation today, I want to talk about what we know about cognitive load, research and assessment, what is currently being done in workplace assessment practice, and what are some of the things that as a community we should pay attention to. Here are 4 questions or 4 items that I will be going over during today's presentation. What's cognitive load and how to measure it? What can we learn from other fields? How other fields have implemented or developed or standardized approaches for cognitive load assessment? What's missing in the field of workplace ergonomics? And then I want to dedicate a part of the presentation to providing some recommendation for practitioners. What practitioners can do today to better implement cognitive load assessments in their practice. For those of you who may not be familiar with cognitive load, it's a demand for cognitive control imposed by a task. Think about a situation like a hospital floor or a manufacturing floor, where there is the operator, attending to their tasks. At the same time, there may be human-to-human communications with other workers. There may be human technology communications with all the devices that the worker may have to use for their tasks. Um, all of these factors, they require attention and memory. So it could be working memory, dividing attention among multiple tasks, sustaining attention, especially for like longer period of time. And so all these factors, they burden, and they sort of, the product of all these factors, they create sort of the result, cognitive load. Some of you might be familiar with this conceptual model. It was developed after the sort of Yerkes-Dodson law in the early 1930s. But in the context of cognitive load and performance, we can envision performance on the vertical axis, cognitive load on the horizontal axis. Um, Whenever cognitive load is low, we see boredom or vigilance decrement, for example, and we know that those factors are bad for performance. Likewise, if whenever cognitive load is high, we may see distraction or mental stress. And at the same time, again, those phenomenon, those factors have a negative effect on performance. So there is sort of this sweet spot in between low and high. We call it optimal, where within that sort of window of cognitive load, performance is high. So we know that conditions of high load are very detrimental for safety. There is some evidence showing that conditions of high load, high cognitive load, increase the injury risk by up to 30%. Likewise, conditions of low load also have a negative effect on performance. Think about contexts like air traffic control, for example, or like control rooms in general, even in nuclear power plants or power plants in general, where operators need to maintain vigilance over time in case when they experience conditions like low load or boredom, for example, that situation can lead to missing important events or warnings and slower response times. So low load, unlike high load, they're both sort of negative. They have a negative impact on performance. So, workplace ergonomics for many, many years has been looking largely as physical factors. One reason for it is because physical factors, they tend to be sort of easier to, or, more easier to measure. At least some of them are. There's been less attention being dedicated to cognitive factors. One of the reasons why is because they're relatively harder to measure directly. So here's some data from our own research program here at U Windsor. Um, we saw, for instance, that completing manufacturing tasks under conditions of high load, they result in 66% longer task times during fine motor assembly tasks and up to 25% longer task time in the context of like what I call like full body motions. There being manufacturing tasks where the manufacturing operator has to move about the workstations, or even healthcare tasks where again the healthcare practitioners, or sorry, practitioner, they have to move around their sort of workplace. It goes without saying, of course, that longer response times that have very negative effects, especially in sort of situation like manufacturing, where those jobs are highly sort of regimented. Other evidence on the negative effect of high load on performance and human performance and task performance come from these other studies that we ran a few years ago. And we saw that because high load results in longer response times, longer task times, uh, workers have to take more time to complete this task. And because they take more time, there is more like muscle expenditure. In this study, for example, we see an increase in 10 to 20%. And these, of course, are particularly dangerous in situations like road transportation, healthcare, and constructions that are environments and workplaces that are already accident prone. So increasing the cognitive demands on the worker makes not only safety but also task performance like worse. I think everybody here would agree that cognitive factors are not easy to measure. So over the years, the community have developed either indirect or surrogate ways to get to cognitive factors, to measuring these factors. For this presentation today, I want to focus on at least a couple of buckets. I bet a lot of you may be familiar with some of this. The first bucket of current approach is those expert assessments. I call them expert assessments because they're administered by experts. Um, a lot of these assessments are sort of oftentimes completed post accident. So there needs to be sort of a claim or an accident to occur in the first place in order for either the employer or the claim owner or the health and safety professional or clinicians to administer these tools. An example of these tools are a checklist. Here you see an example from WorkSafe BC of a cognitive job demand toolkit. As you can see, there are under cognitive demands, there's a list of items that are oftentimes assessed from problem solving, for example, verbal communication, multitasking, etc. So using a tool like this, the expert, again, a claim owner, maybe sometimes the employers themselves, they kind of fill out this form, including information about the frequency of the duration and more information about the task description that associated with, for example, an increase in multitasking. Now, although these tools are very valuable because they shine a light on the importance of cognitive load, they do have some limitations. Oftentimes, these tools are applied post-accident, so there has to be an accident to occur in the first place in order for these tools to be deployed. As a result, they have limited use for workstation or workplace design. More importantly, is that they only provide one single snapshot. So whenever an accident occurs, the expert assessor come in and they apply these tools, meaning that even if, say, the average cognitive load or cognitive demand associated with a task may be okay, because this information is only captured once, it doesn't account for spikes in cognitive load resulting from like environmental factors, for example. And more interesting, what is causing these spikes in cognitive load that perhaps are the one leading to the accident. As much as we want, these, or is ideal for all these experts to have like a similar training, and consistent training in applying these tools, there is still some variability there, or at least there may be some variability between assessments. So assessment may vary depending on who completes it and depending on if it's an employer or it's a claim owner or etc. They may have different background and training that may sort of provide inconsistent findings. And of course, it goes without saying that because of that, they rely on self-reported assessments. So there may be situations where cognitive job demands may be intentionally or accidentally over or underestimated. The second bucket is the one of self-reported metrics. A lot of you may be familiar with at least the first one, NASA TLX. There are other similar scales like the SWOT or Simplified Workload Assessment scales. In case you're not familiar with NASA TLX, it's a pen and paper approach. It has 6 scales, one of them measuring mental demand, physical demand, temporal demand, etc., on a scale from 0 to 21. The way it works is that in this case, is the worker themselves that fill out these scales. Now, because of that, a possible limitation of these approaches is that ratings may be intentionally or accidentally over or underestimated. So although having these tools today is very valuable to conducting cognitive load assessments in the workplace, but again, my personal ratings may be different from another worker's ratings. So that inconsistently plays a role in how valid the findings may be. And as a result, how the interventions that are developed based on those findings are. Another limitation of this approach is that workers have to stop their job duties to complete it. So they're intrusive. Workers, they have to pause what they're doing and then fill out the assessment. Also because of how the assessment, these sort of subjective sort of self-reporting scales are designed, there's not a lot of value in sort of, or at least is logistically challenging. It's logistically challenging to complete these assessments, like repeatedly. Let's say every 5 minutes or every 10 minutes. That's sort of logistically complicated. And of course, because of what we discussed so far, there are some issues around the validity and generalizability of these findings of the ratings. There may be some variability between workers, even within the same workers. They may produce different ratings over time, and so the robustness of the findings, and as a result, the robustness of the interventions that developed upon may be sort of limited. So I want to move on to the next sort of step in this presentation. As I said, we had the fortune to work with Atlas Copco for a number of years, and through these collaborative work, we have zeroed in our attention on eye metrics as a way to more reliably capture cognitive load. One metric that we looked at is blink rate, how often and how quickly we blink our eyes. The more frequently we blink, that's usually an indication of greater cognitive load. Here's some data from one of our studies where we had an easy cognitive task and a hard cognitive task. And we see sort of consistently how a blink rate increases as cognitive load increases. Another measure that we looked at is pupil size, which is the ever-changing size of eye pupils. Unlike blink rate, which is somewhat controllable, voluntary controllable, pupil size is not. It's a lot harder to, if not impossible, to voluntarily, control the size of our eye pupils. And again, studies from our findings from our own research, but also from the broader human factors and ergonomics literature show consistently how pupil size tend to increase with greater cognitive load. Now, there are some, benefits of using these metrics. They tend to be objective. As I said, you know, pupil size in particular, it's very difficult, if not impossible, to control. So as a result, some of these metrics may be less susceptible to voluntary control than the other sort of pen and paper or expert assessment tools that we discussed prior. Um, in the last few years, measuring these metrics has become less and less intrusive. Here's a picture of a study participant wearing like pupil labs glasses, and unlike the way that eye tracking equipment used to look like, you know, even not that long ago, in today's world, this equipment has become not only less intrusive but also more or less inexpensive. This is like a big plus for pupil size is the high temporal frequency. So being able to track cognitive load with a millisecond accuracy, it really provides very rich information on how specific subtasks, or in the context of interface evaluation or workplace evaluation, having the worker complete specific subtasks, or even the way the design of an interface looks like, having these temporally accurate information, we can really use that to pinpoint what specific, subtask or design features in an interface, for example, are yielding more cognitive load, higher cognitive load. In our research, we also found that these metrics are accurate even in full body motions environment. I have a couple of short videos here. The one you see on the left is from a study that we conducted in collaboration with our TRQSS, a local seed manufacturing partner. The worker, she's wearing the eye tracker, and you can see her eye movements, using that, looking at that like red circle. And so those are fixation. Then you see the lines being those eye movements, and how the accuracy, even during those kind of very demanding full body motions, the tracking was very accurate. On the right hand side, you see a study we conducted in a simulated environment, where you see there it's a mannequin. And again, here the participant was wearing the eye tracker, and the accuracy that we got from using this tool was, really high. So these are the plus of these metrics, that today's produce high accuracy even in like a very dynamic workplaces. Now, it goes without saying that using this technology comes with challenges. The first of them is that they do require equipment. So even though some equipment has become more affordable over the years, they still require, purchasing equipment. And maybe, the other sort of main shortcomings, the data processing. Now, it's true that using eye tracking, they do require some data processing, but at the same time, there are more solutions on the market that they promise to reduce the data processing involved in these sort of like required for this equipment. So that would make sort of data processing less laborious, and maybe not requiring the researcher or the practitioner to have, you know, technical expertise. Here, what I see here is an example of a study that we're working on at the moment and uses machine vision for detecting object classification and glances during driving. I'm showing you this video because again, it's an example of a study where we're doing away with scientific eye trackers. So in this case, we're only using like a generic cameras. The video of the driver comes from like a dash cam. And so in this case, we didn't use any scientific grade eye tracker, but we use machine vision to do object classification and glance classification. So in this video, you see all those like lines going up and down. Those are the different, for example, the eye movements or the object detections. Then we're able to process using machine vision algorithms from a generic camera video footage. So this is just an example, but as I said, there are solutions out there that would help alleviate that technical burden on the practitioner, for example, in using this technology. The work that we've done comparing eye tracking and machine vision algorithms using generic camera video footage side to side prove that these processing that doesn't require eye tracking is actually very accurate. When we put these two solutions, eye tracking and machine vision side to side, the patterns of data that we find are very consistent, which is very good. Now, of course, it goes without saying that in the context of driving, these may be more successful because we have again a driver that is in a sitting position all the time and the camera pointing at the driver all the time. So from a logistical standpoint, these sort of situations, they're sort of like ideal for this type of like machine vision processing. So moving on to the next step in this presentation, I want to, want to sort of think about what, as a community, we could do better. I think about what other fields have attempted to do in terms of cognitive load standardization or design guidelines, for example. A lot of the research that, first of all, the research that there is available, a lot comes from road and air transportations. But again, I want to share a couple example with you just to give you as an evidence that other fields perhaps have attempted to do more in the context of like standardization or design guidelines. The first example comes from road transportation and driver distraction research. In the U.S. Department of Transportation and together with the International Organization for Standardization, they've developed these DRT or detection response task. So this is an ISO standard for measuring cognitive load. How does it work? It's a simple reaction time task. So as you can see in the picture, the driver there is that is wearing that headset, and there is a DRT light. It's a simple LED light that that turns like red every so often. Whenever the light turns red, the driver has to push a micro switch. Reaction times to the light and the accuracy are recorded, and these information provide accurate estimates of a cognitive load. Here, for example, you see like data from a study we conducted years ago where we used the DRT to measure the cognitive load imposed by different tasks. So These reaction time, task, and accuracy data together, they provide accurate information on cognitive load. From the design standpoint, again, I borrow another example from road research. In 2012, the US Department of Transportation set guidelines for visual and manual distraction. They were interested in answering the following question: how long can driver looks away from the road before that task become distracting? Now, it is important to note that these design guidelines were developed in the context of measuring the distraction potential of in-vehicle electronic devices. So those touch screens, interfaces that everybody have in their vehicles. I'm not going to go into the nitty-gritty of these guidelines, of course, but in this case, the US DOT developed some thresholds, saying, for example, that off-road glances, so individual glances away from the road, shouldn't be longer than 2 seconds, and that the total eyes of road time shouldn't be longer than 12 seconds when interacting with these interfaces. So whenever these interfaces required either off-road glances longer than 2 seconds, because again, looking down at the touchscreen, or a total time of off-road glances of 12 seconds or more, that interface would sort of fail the test. The last example I want to bring to your attention, the one of Perclos. This is found like a wide adoption in road and air transportation. The idea with Perclos is, they look at eyelid opening and is a standard approach for alertness. Again, alertness, not cognitive load. But again, this is one approach that again I found so much application in air and road transportation, and it's been around for like 40 years or more. And again, it represents a standardized approach for measuring alertness. So what's missing? So given everything that we discussed today, what's missing in sort of workplace ergonomics assessment? We lack a clear definition of what high and low cognitive load even means. I show you this conceptual model at the beginning. Although we say low, optimal, and high, there's no exact thresholds of what constitute low load, optimal load, or high load. We lack a universal standardized approach for measuring cognitive load across workplaces. We do have some tools that we may use, but again, we don't have guidance on what specific workplace is conditioned to use one tool versus another. There's more advancement done in the wearable and AI and machine learning that we can leverage to provide more accurate, highly temporal frequency solutions for cognitive load measurement in the real world. The third point is intervention strategy. Even when we find conditions of high load or low load, what do we do about it? So there needs to be more sort of concerted effort on targeting intervention strategies. What should we do to make sure that low load or high load are mitigated in terms of job design, technology, or environmental designs? There is need for guidance on design strategy before even we get to the point of an accident occurring. How can we design workplaces, devices, etc., to reduce the risk of an accident even occurring? So the need of design the guidelines for jobs, workstation, or device that can be used proactively. And last but not least is prediction forecasting tools. We have prediction forecasting tools in a lot of industry in today's world. Think about a weather forecast, where there's these humongous models, statistical models predicting weather, or traffic flows. Whenever there is like a big event or a weather, weather conditions, a lot of these sort of traffic data are pulled in to address potential, high volumes of traffic proactively. Some of hospitals are using already these models to predict peak times, for examples, depending on the weather, the season, the time of the day of the week, etc. So the idea is to use this sort of macro organizational data with micro um, worker sensors data coming from wearables, for example. So fusing this macro with micro data, we can develop more better and more accurate forecasting tools that can predict, conditions of, peak load, for example. The last part of this presentation, I want to talk about some practical recommendations that today's practitioners can use in their, you know, cognitive load assessment efforts. Even with the known limitation, existing pen and paper or expert approaches, they have values. NASA TLX or cognitive job demands, they have value because they shine light on the cognitive job demands associated with workplace tasks. So my recommendation is to still continue to include these assessments. The second recommendation is what I call here rinse and repeat. Oftentimes these assessments are only performed once or a few times. And given the inter-variability issues associated with NASA TLX, for example, or even the cognitive job demand toolkits, there is a need to apply these assessments more than once to more than one worker, for example, to more than one day of the week, to more than one shift. So the more information is gathered, the more rich that data set and the findings will be, and the more accurate the interventions may be. Also, in the whenever we sort of assess the workload associated with workplace conditions, not only focus on how that combination of task or technology, etc., but also looking at how individually different job tasks or different technology or different components of that job affect cognitive load. The third recommendation is triangulate, triangulate, triangulate. The idea is that only applying NASA TLX individually or expert assessments like the cognitive job demand analysis individually, although they have value, but there needs to be sort of brought together with, for example, observations as well. Not only because it's possible that the more data we have, and the more sort of these data from these three different tools overlap with each other, but also because tools like NASA TLX, they may only be able to uncover a portion of the issues. Same thing for expert assessment, same thing for observations. So being able to bring all these tools together on one assessment provide more richness to the data, provide more validity. And as a result, the findings and the interventions are more robust. And then don't wait until things go wrong. So the idea is to be proactive in the assessment of workplace changes. So if there is a new hire, new machines, new interfaces, new workstations, be proactive in looking at the workload associated with these with these new changes in a way that so not only wait for the accident core, but also design accordingly. And again, so this is a fifth recommendation. Before something new is introduced in the workplace, use the tools, the expert assessment, the NASA TLX, the cognitive job demand, etc., even on like a subset of workers, just to get a better idea of how a new design change or a new workplace change is going to affect cognitive workload. The last slide is, this is sort of what been through my mind preparing this presentation is like, given that there is that missing link between research and practice, what needs to happen. I know there are a lot of associations, like ISO, for example, a lot of organizations like CRE-MSD, ACE, etc. They're very active in, in ergonomics sort of research and practice. But, what I would like to see, I think, in more of a like a concerted effort on cognitive ergonomics, like a workforce on cognitive ergonomics, to look at those issues. Lack of standardization, lack of clarity about interventions, about design, so that we can really make more like concerted progress on it. Prioritize actionable items. Some of the items that I listed that they're missing, some of them have higher priority, for example, like creating a standardized tool that everybody can use, or standardized or intervention guidelines. There may be other items, like, for instance, those conceptual model that may have lesser priority. And then the third step is act. So I really would like to, leave you with, having practitioners, researchers, government employees here in this call. I really hope that, again, we can actually, you know, see more actions, like concerted actions in this field. And that's it for me.
Thank you so much, Francesco. That was a fantastic overview. So at this point, we're going to be taking questions from the Q&A feature. So we've already had a couple questions come through so far. The first one, Francesco, the comparison with pupil size and blink rate. How was the low and high cognitive task categorized? For example, was pupil size and blink rate checked against NASA TLX? If not, how did they categorize the task as being of low and high cognitive demand?
So in that case, this is a great question. In that case, it was sort of experimental conditions. So in that case, we designed those tasks in order to, one was less complex than another. So we kind of artificially designed, those two tasks, one to be easier and one to be harder. And as a result, our effort in that case was, we were interested in understanding how well blink rate and pupil size tracked, so those difference in task demands. As for the other part of your question related sort of triangulation, yes, oftentimes we use multiple metrics. So there is evidence that in some scenarios, physiological metrics track uh, adequately with NASA TLX approaches. But again, the relationship between physio and subjective, or self-reported, is not very linear, is not very clear. Um, for example, there are many instances where, um, you know, if we repeat using NASA TLX many times in a short period of time, there are some human, like the participants or workers, they just lose interest, and they kind of, at the end, you may end up with, a lot of ratings being either half a way through, like on a 5 on a 10, 5 out of 10, because, again, the repeated exposure to the tool, the fact that they may not be that interested in filling out that scale after repeated exposure. So there is, over time, there is less accuracy associated with those pen and paper tools.
Great, thank you. Have you looked into how time pressures are affecting effort responses? For example, the manufacturing worker you showed. You spoke about how tasks can be longer, but I'm interested from the other side, where time to complete the task is fixed.
Yeah, absolutely. I mean, time pressure is one big driver of cognitive load. Um, in the context of manufacturing, for example, there's a lot of factors that go into task completion. Time of the day, the point in time during the shift. It could be early on or later. It could be different workers, etc. So to answer your question, generally speaking, yes, there is research looking at the effect of time pressure and time limits on a cognitive load. And again, they usually a positive relationship between the two. When it comes to sort of adapting workplace sort of interventions and designs to cognitive load, is always sort of being able to, as far as possible, as realistically as possible, take into account what factors go into cognitive load. Is it sort of the different workers? Is it, as I said, is it the time of the day? It could be, maybe the worker is using new tools or etc. Or there's a new design of the workstation, etc. Having sort of a better understanding in how all these sort of factors affect task completion times, and perhaps account, in determining task times or cycle times, being able to account for all these factors. I think there is value there. So the point, cycle time, for example, they tend somewhat to adapt to the characteristics of the workers or of the workstation, like more sort of punctually. Yeah.
Great, thank you. Would individual capacities affect what low, high, and optimal cognitive load should be? I could see that as being part of the problem in determining clear definitions. Some people seem to thrive when demands are higher, when others seem to struggle.
Yeah, definitely. I mean, we see that in physical ergonomics as well. Again, I'm not the expert there, but we see that as well in cognitive ergonomics. So there is some individual capacity that may affect how cognitive load. There's a lot when it comes down to humans. There's a lot of variability, not only between individuals but also within the same individual. I'm giving this presentation at noon today. If I were to give this presentation at 7 p.m. today, it would be very different, at least for me, because I'd be more fatigued. So to your question, yes, there are individual differences, but of course, when designing for like adopting like a universal design approach, um, you know it's possible to define sort of bandwidth that can accommodate both the low capacity, for lack of a better term, with and the higher capacity individuals. So there are differences, but also there are ways to sort of accommodate both, sort of using like a universal design approach.
Great, thank you. How can researchers and practitioners advocate for a preventative approach to workplace health and safety at the policy level? What kind of collaborations are needed to signal to leaders to value this work before the injury occurs rather than after?
Well, there's a more and more data showing the importance that cognitive load plays into injury risks. So from like a data perspective, the more and more we learn, and the more and more we gather data, the more and more we can use these data as evidence that cognitive load is a key component in workplace design. So I feel like, unfortunately, sometimes something bad needs to happen in order for sort of the community, society, to shine a light on it. So the more and more evidence there is, even not only at the sort of federal level, but even at the company level, the more and more evidence we can gather to say, okay, well, in this specific situation, we saw a decrease in, performance, there being either longer task times or lower accuracy or increased, like fatigue levels among workers. So I think the data and evidence part is very important. When I was preparing this presentation with Kim, we were sort of chit-chatting about some of the limitations that are inherent to cognitive ergonomics. because these cognitive factors, they're hard, it's hard to put your finger on them. So as a result, it's sort of a challenge among cognitive ergonomics researchers and practitioners to convince government or employers, etc., that is important to look at these issues, and they have like a practical value. Because if we look at these issues, if we design our devices, our workstations, our workplaces in a much more like human-centered way, we can actually see improvements. So I think, again, having data, having evidence at the organizational level, or at like more like the broader sort of national, provincial level, I think that's an important first step. And once again, we have more of this data. And when we have this data gathered, I think joining that with what we know about the negative effect of cognitive load on performance and safety, I think the two, can, hopefully be better used to make like a stronger case. But also, and sort of, I finished up this question answer here, having more opportunities for researchers, practitioners, government partners to communicate. And I think that I would like, in my sort of ideal utopic world, I would like to see sort of more concerted efforts, even if they're driven from the government or like industry associations, but more sort of concerted effort to looking at these very issues, collectively.
Yeah, that's a great idea. Great points there, Francesco. There's quite a few questions in here, so I'm going to try to get to as many as possible. Is anyone using EEG brain wave monitoring for assessing cognitive workload?
Yeah, absolutely. I mean, there's a lot of folks doing that. Again, our decision for looking at eye metrics is that they tend to be less intrusive these days than EEG, even if without going into the details, but even if we use like a dry EEG sort of sensors that do not require sort of gel or a lot of like preparation. Um, Again, as far as I know, anyway, they still have they require like more intrusive sort of work. So the workers have to wear these sensors, and even on the processing side, I think they may require some like more processing labor there. The reason for us to pivot to eye tracking is because, again, especially today's, they tend to be not as intrusive that they used to be. The price of the tool that we use, like Pupil Labs, is relatively affordable, and even on the data processing side, the data processing labor tend to be less than that of like EEG or like brainwave techniques.
Makes sense. Do you think automation usually reduces cognitive workload, or does it more often redistribute it into monitoring, vigilance, and exception handling?
So that's a great question. I mean, there is this concept, it's called the paradox of automation. Whereby we tend to increase automation because we want manual labors to be reduced, and and human to be less involved in the process. But then when we introduce automation, we need to rely more on the human when things go wrong. You see a similar concept, a similar phenomenon right now with AI being introduced not only in the workplace but in our society, where initially it was like, well, AI is going to replace humans, but now I think there is a more of a reckoning in the industry, across industries, where we see AI more of an assistant rather than a human replacer. So in terms of like cognitive workload vigilance, although we have great examples of automation in our society that are working great, just banal examples are like elevators, for example. When you step into an elevator, you don't need to monitor what's going on. But of course, there are other examples where automation may not be as perfect and not as reliable. In that case, introducing automation instead of decreasing workload and taking the human out of the equation even puts even more burden on the human because they have to maintain vigilance, and vigilance is takes effort. You see, for example, in semi-autonomous cars like Tesla, Autopilot, and the likes, where although this technology has gotten better, but it's far from being like bulletproof. So instead of like reducing the burden on the human, they increase it because ultimately the human is the one responsible.
Very interesting. Okay, how well do these eye tracking technologies correlate to the NASA TLX subjective measure?
Yeah. So again, um, they do to some extent. The problem with NASA TLX metrics is that they, especially on a repeat sort of measurement, like a measurement to measurement, they become less and less sensitive. They become less and less valid. So if you do assessment once, you may see somewhat of a reasonable correlation, but as you test and retest, or as I said, rinse and repeat, as you continue to use the same tool and one tool only over times, it loses sensitivity. Again, users may just get bored and say, well, I'm just going to fill it out without even looking at it. And we've seen that in a lot of studies. So the short answer is at first, you may see sort of the two correlated reasonably well, but over time, they become less and less sensitive.
Okay. Have you asked the Canadian Standards Association to work on a cognitive ergonomics standard? They already have an ergonomics document and perhaps still, oh, and yes, they do have the one on office ergonomics. I'll confirm that one. So there's an ergonomics standard as well as an office ergonomics standard. So have you looked at requesting maybe development of a cognitive ergonomics standard?
Yeah, I have the fortune of just recently just sitting on the ISO and the SC, I think it's called SCC, if I'm correct, the Canadian like Standard Association, on that committee, on the very committee, and so I'm hopeful that more can be done in the future. So even thanks to the presentation today, and I'm hoping that we can and sort of gain momentum to see more sort of more practical actions you know being taken in the future.
Very exciting. Glad to hear that you're a part of that. I like the idea of a national workforce for cognitive ergonomics. Give me an idea of what that would look like, who would lead it, example, NRC, ACE, etc. What are your thoughts?
Yeah, so all right. Well, I would see definitely, researchers, industry, and government sort of be involved. Um, I'm, these could take the shape of like several shapes. I think there needs to govern right now we're at a point where there needs to be sort of these need to be driven by government. Um, because of course they have the capacity to, bring all these people together and to, have these people kind of work together on this topic. So having sort of representative from researcher industries, different industries also, health and safety, etc. I think that the way and driven by government, I think that's the way uh, you know would look like. I think, as I said, there has to be sort of prioritization of what's missing, or what are the items to be worked on. I think having starting to look at how to standardize cognitive load assessment. I think even if it's just, looking at the tools that we have currently available and having sort of a decision or determination on what are the best tools in what situation, I think that would be a great start. And then, using that information to start developing workplace interventions. I know that on the industry side, there's a lot of um, companies that that have their own sort of working groups on these topics. A lot, of course, in the automotive industry. So I don't see necessarily the need for government to lead these efforts on the long term. I see in examples in automotive. Take up for example about the crash worthiness, the like NCAP safety ratings, where in that case is not the government enforcing safety ratings by sort of industry associations. So to make it short, I see governments sort of having to lead these at first, and then hopefully as we sort of educate our community, our industry partners more and more, maybe there is a room down the road for sort of industry themselves to continue this effort because they are the ones ultimately who can have like a direct effect on how systems are designed.
Great, thank you for that. So I'm just being cognizant of time. We're at 1 o'clock now. We won't be able to get to all the rest of the questions, but Francesco has agreed to work with us after the webinar to provide written answers to those questions. So thank you for doing that, Francesco.
Yeah, absolutely.
We will send those out to the registrants following the webinar. And just as a closing, I just wanted to thank everyone for joining us today. And we look forward to seeing you at our next webinar. So please check the events page on the CRE-MSD website for the list of upcoming webinars. And finally, if you haven't already, we encourage you to visit the MSD Prevention Guideline for Ontario website. This is at msdprevention.com, and you can find a range of resources designed to support workplaces. Have a great day, everyone, and thank you again, Francesco.
Yeah. And if you for those of you who want to reach out to me directly, they can find my contact on the University of Windsor website.
Great. Thank you so much.